Hi Anika, welcome to the presentation. So, I understand that you will be talking about the Lebesgue Number Lemma, um, which is to give some context to the other people who are viewing this. We were discussing something related to covering space theory, and in the covering space theory, which is part of algebraic topology, one has to prove that there is something called a lifting of a path. Now, when you in certain kind of spaces, so when you try to prove that, you have to use this very fundamental result from real analysis, which is known as the Lebesgue number lemma. And it's very beautiful in the sense that it sort of brings together many ideas from point set topology, real analysis, and stuff like that. And today I'm very happy to say that we have a student, Anika Chopra. She is in grade 12. I think she lives in Gujarat. Is that right? You live, yeah, I
Yes,
think
I
she
live in
lives in Gujarat, India, and she has been working with us in the hyperbolic geometry work group for some time. And today she will be presenting this particular thing, the proof of Lebesgue number lemma. So over to you, Anika. You can start whenever you like.
Great. So thank you so much for the introduction. Today, as Sir said, I'll be talking about how to prove the Lebesgue number lemma. Now, this is a very elementary proof once we've defined a few ideas. So let's begin. The Lebesgue number lemma was discovered by Henry Lebesgue somewhere around the late 19th century, and it's very useful in the study of compact metric spaces. One application of the lemma is that it's used to prove another very fundamental result when it comes to compactness. So it's used to prove that a sequentially compact metric space is also covering compact. Now in this presentation, we'll be going over some preliminaries which will help us define the statement of the Lebesgue number lemma. Then we will move on to reviewing some basic results which will lead us to the proof of the lemma. So let's jump right in. Now, just before I start defining some terms, I would just like to say that a lot of you watching may already be familiar with them. So I'll try and run through them as quickly as I can because they're still very important in defining the lemma. So firstly, let's talk about an open ball. So we have x comma d. We have a metric space x comma d, which is essentially a set equipped with a distance function, and we define an open ball centered at a point x in the metric space x, with radius r as the set of all y and x, such that the distance between x and y is less than r. So notice that when we're defining an open ball, there are two parameters that we have to specify: the center of the ball, which is the point x, and the radius. And in this diagram, you can see that y is contained in the open ball b of x comma r, since b of x comma y is less than r. And another example of an open ball in the real line equipped with the standard Euclidean metric is just the open interval x minus r comma x plus r. The proof of this is very easy; it just follows from the definition. So I'll leave it to you to think about. So now let's talk about open sets. So a subset S of a metric space X is said to be open if for every point in S that exists in R greater than 0 such that the open ball B of X comma R is contained in S. So you can think of an open set as a set where every point in the set has an open ball around it. And it's also very easy to prove that an open ball is an open set itself. And again, I'm going to leave the proof to you because it's very elementary. Now let's talk about open covers. So an open covered U of a set X is a collection of open sets such that X is contained in the union of those open sets. And a subcover of an open cover is just a subset of this collection of open sets U, such that this subcollection also covers X. And I'm going to show a diagram in the next slide, which will hopefully make this a bit more clear for those unfamiliar with these terms. So now let's talk about compactness. A metric space X is said to be compact if every open cover of X reduces to a finite subcover. So as you can see in this diagram, on the left we have an open cover, and on the right we have a subcollection of those open sets which also cover the entire metric space X. So now that we've defined our most basic definitions, let's move on to what a Lebesgue number is. So we let x comma d be a metric space and u be an open cover of x. Now, if there exists a delta greater than 0, such that for all elements in X, the open ball centered at X with radius delta is contained in A for some open set A in the open cover, delta is said to be a Lebesgue number for you. So, in other words, it's just like if I have an open ball in the anywhere in this metric space with radius r, that is completely contained within one of the open sets. And it's also very easy. It's very intuitive to think of a Lebesgue. So if delta is a Lebesgue number, then any number less than delta will also be a Lebesgue number. And a metric space X is said to have the Lebesgue number property if every open cover of X has a Lebesgue number. So now we've defined everything we needed to move on to the statement of the Lebesgue number lemma. So the Lebesgue number lemma states that a compact metric space X comma D has a Lebesgue number property, and this is equivalent to saying that every open cover U of a compact metric space, for every open cover U of a compact metric space, there exists a positive real number delta, which is called a Lebesgue number, such that every open ball B of x comma delta around a point in the metric space is contained in U. Um, so again, we have the diagram depicting that R is the Lebesgue number for U. So now we can go on to some basic results, which will ultimately lead us to the proof of the Lebesgue number lemma. So again, I have a few more definitions, which again are quite common and you might be familiar with them already. So a function from a f from a metric space x comma d to a metric space y comma d prime is said to be continuous if for each epsilon greater than 0 and each x and y in x, there exists a delta greater than 0 such that d of x comma y less than delta implies that the distance of the images of those 2 points x comma y is going to be less than epsilon. And we have an equivalent definition of continuity in topology. So a function from a topological space x to a topological space y is said to be continuous if the inverse image of an open set in y is open in x, and also if conversely if the inverse image of a closed set in y is closed in x. So here we can see that v is an open set in y and the inverse image f inverse v is open in x. So yes, so now we have Lipschitz continuity, which is somewhat of a stronger kind of continuity. Now, function in a metric space from a metric space x comma d to a metric space y comma d prime is said to be Lipschitz continuous if there exists a real constant k greater than 0, such that the following inequality is satisfied. And for those of you familiar with the idea of uniform continuity, which is basically when the same delta works for each epsilon, and like the delta that we chose previously is independent of x and y. Um, so the Lipschitz continuous function is uniformly continuous, and in that case, delta is going to be equal to epsilon over k. Yeah, so now we are going to define the distance from a point x to a subset of a metric space A. So let x comma d be a metric space and A be a non-empty subset of x. Now for each element of x, we define the distance from x to A as the infimum of all the distances from x to any point in A. This is going to be important, very important for the proof of the Lebesgue number lemma. And we propose that this function d of x comma a is continuous. So this can be proved using just some basic properties of metric spaces and the definition of Lipschitz continuity. So by the triangle inequality in a metric space, we have the following inequality. So we know that d of x comma small a is going to be greater than equal to d of x comma capital A by the definition. We took d of x comma a, capital A to be the infimum of all d of x comma small a. And by the triangle inequality for metric spaces, that d of x comma a in turn is going to be less than or equal to d of x comma y plus d of y comma a. And thus we can make a few rearrangements and obtain that d of x comma a minus d of x comma y is less than d of y comma a. And again, we rearrange to obtain the last inequality. And notice that this establishes what we intended to prove, because this is just the Lipschitz, the expression for Lipschitz continuity with k equals 1. So I don't think that is visible on the screen, but I hope that's clear. So now we're going to move on to the proof. We have all the ingredients we need, and we just have to put them together. So let's set up the proof first. We let x comma d be a metric space, and we let u be an open cover of x. And oh, sorry, x comma d is not only a metric space; it's a compact metric space, and u is an open cover of x. Now, since X is compact, there exists a finite collection, A1 through AN, subcollection of U that also covers X, because in a compact metric space, every open cover of the space reduces to a finite subcover, and hence we have the second point. Now we define Ci to be the complement of all Ai, and we define a function going from x to close 0 comma infinity as follows. And now we're going to make a few observations about f. So the first observation is that since the function d of x comma capital A is continuous for a fixed a, and f is just the sum of d of x comma capital Ci, it is a finite sum of continuous functions and therefore is continuous. So now we're going to use something called the extreme value theorem, which states that a continuous real valued function on a compact metric space takes on a maximum and a minimum value. So this theorem guarantees the existence of a delta such that for all elements in X, we have that f of x is greater than or equal to delta. And now we're going to examine some properties of delta. The first being that delta is always greater than 0. And notice that since delta is just the minimum value that f of x can take, it suffices to show that f of x is greater than 0 for all x in x. And how will we show this? First, we'll choose an I such that for any x belonging to the metric space X, X is contained in AI. Now, since AI is an open set, there exists an epsilon greater than 0 such that the open ball centered at X with radius epsilon is completely contained within an AI. And notice that this is also equivalent to saying that d of x comma ci is greater than epsilon, since ci is the complement of ai. And from that, we have that f of x is greater than or equal to 1 over n times epsilon. And how do we get this? Because um, each d of x comma ci is going to be greater than epsilon. So that is going to the final inequality will f of x will finally be
Hold
greater
on.
than or equal.
Wait. What happened here? So each of the d of x comma ci, you're saying
Yes.
that's greater than epsilon? Well, what's
Yes.
happening? Why is that?
Because, so b of x comma e is contained in ai. So if we imagine the open set ai, we have the open. Sorry, we have. I won't be able to annotate on the screen, but so for the open set ai, we know that there exists an open ball with radius epsilon, such that b of x comma epsilon is contained in ai, and since everything in ai, so since
So
the
I
maximum.
understand from d. So I understand that d of x comma ci for that. Let's say I is equal to 5. Okay.
Yeah.
So d of x comma the distance of the point x from ci or c5 is greater than epsilon. That is
Yes.
fine. But what about the other ones?
Yes. So you're asking how does this follow from the previous, like how does the final inequality follow from the previous thing that we said?
Right.
So basically, so we have the sum over k from 1 to n of d of x comma c of k. So we have n, like, so d of x comma c1, d of x comma c2, all the way up to d of x comma cn. So we have n such terms. So each
Right.
of them are individually less than epsilon. So the total sum of them is going to be
Why is
less
that?
than
Why is that?
is going to be um because each of them is greater than epsilon. Sorry, I made a mistake. Each of these in d of x comma ci is going to be greater than or equal to epsilon, and we have
Why is that? Why is that true?
because b of x comma epsilon is contained in ai, so the distance between x and the complement of ai will be greater than epsilon. uh,
So
should I
are you
explain?
taking so what you I think what you are missing here probably is this, that this b of x comma epsilon
Yes.
is contained in every AI.
Oh, yes. Um,
It's not that
uh,
it's contained in one, because there are finitely many of them, right? Let's say n
yes.
equals 10. Let's say, suppose there are 10 of them. Okay. So A1, A2 up to A10 maybe.
Yeah.
So you maybe you have to reduce epsilon a little bit. That's
Yeah.
fine. You start with one ball, it's contained in A1. You reduce it
Hmm.
a little bit more, it's contained in A2. Since there are finitely many of them, then you can find an epsilon such that this is contained in all of them, right?
Yes.
That's the, so you're missing, what you're missing here in the second line is that for all I from 1 to n actually.
Yes. Okay.
So
So we need to say that epsilon works uniformly for all AI, and that would from that it would follow that I mean, since every d of x comma ci is greater than or equal to epsilon, we the sum over all of them is going to be greater than or equal to n times epsilon, and then that's just epsilon, and we know that epsilon is greater than zero. So that proves that delta is also greater than zero. And
but wait,
yes,
there is still a catch though, because x might not, so you're starting with one x, right?
yes,
So you might not, I mean, all the AIs might not overlap,
yes.
right? So how would you choose x?
So
Or do
x
you,
was
yeah, go ahead.
yes. X was chosen arbitrarily, so we just let x be any point in the metric space x, and then
Right.
we choose I such that x is contained in some of the. So x will be contained in one of the open sets from the definition of the open cover,
Okay, so
and
A1 suppose, yeah.
yes. So since it's open, we are guaranteed the existence of an epsilon which is greater than zero, such that the following relation holds, which is b of
Correct.
x
So
comma
it will
epsilon
just,
is
so it will work for that particular AI, right?
yeah,
So what about the,
and
so how did you choose CI? CI was like
the
one second.
complement of AI.
Yeah, CI was one of the complement of AI, right? Each of the CI. Let me just go there. So CI is AI complement, right? So coming back to this, yeah. So what you are guaranteed is that, let's say that x is contained in A5, then b of x comma epsilon will be contained in A5. So the distance of x, so we already have an answer in the chat actually. That's pretty cool. So the distance of x from C5 is epsilon, or I mean more than epsilon rather. But how does it, you know, work with the other ones? So I'll just, since we don't have enough time, so I'll just give the answer that a commenter actually gave. So the commenter gave this answer. So what he says is that choose x, x1, x2 for each AI, like there will be one xi. Mhm. So if choose one xi from each AI and then choose the max of them, do you think that would work? What do you think?
Yes, so that could work for each CI, and yeah, that would solve the problem. Uh, yes, that I didn't take that into account. I should have. Okay. So
Think about that, because what you would want is you would want to calculate the distance of each of those, because you're trying to find a point fx such that value of fx is greater than 0, right?
Yes.
That's what we're trying to find out. Okay. So you want a point x such that its distance from each of the CIs is greater than epsilon, right?
Yes.
But I mean, surely it's contained in some of the CIs, isn't it? So if it's contained in one of the CIs, then the distance of it from that particular CI is 0, right?
Yes.
So you have to think about this. This is a subtle point. Something is happening here. Okay, so for the sake of this argument, let's assume that such an X exists, such that, but I must say that it is extremely important to show that this is an existence question, whether or not an f of x exists such that it's greater than 0. So I would like you to discuss this with your mentor, Shomode, this particular point, and figure out what's going on. But going forward, let's say suppose such an Sx exists such that its average from the complements of each of the open sets is positive. Okay, what happens then?
So then we've established that f of x is greater than 0, which shows that delta is also greater than 0. And now the next thing we need to show is that delta is a Lebesgue number for the open cover U. And how are we going to show this? We have to show that b of x comma delta is contained in some open set a comma k. And so now we again make some, we take d of x comma cm to be the largest of the values d of x comma ci. And then we have that f of x, which is defined as 1 over n times this summation, is less than or equal to 1 over n times d of x comma cm, because each of these d of x comma ci is going to be individually less than d of x comma cm, and that
Right.
is just equal to d of x comma cm. So f of x is less than or equal to d of x comma cm. And now we're going to combine everything we know from our previous results to come up with this inequality, where we have that 0 is less than delta is less than or equal to fx, which is less than or equal to d of x comma cm. And since this holds, we can say that the open ball centered at x with radius delta will lie in the complement of cm, which is am. And this will be clear from a diagram that I show. So since the distance between x and cm is greater than delta, and notice that the distance is defined as the infimum value of the distance between all x and all elements of cm. And so cm is the complement of am, so that means that this open ball cannot lie in cm, so it must lie in am, and that completes our proof and concludes the presentation.
Okay. Very nice. I think you worked really hard given that you are in grade 12 and just in school and you were trying to pick up all of these words and ideas. I really appreciate the work you did. It shows that you are working really hard, and I must give credit to Shomadip as well. He must have worked hard with you as well, right? So yeah, I think this is pretty good. But I would strongly advise you to talk to Shomadip and clear up that particular point, that what's going on there, because we have to establish you are using the extreme value property of continuous functions on compact sets. So that that requires you to, show that something is positive, otherwise you wouldn't be able to do it. So yeah, very nice work, Anika. Thank you for joining in today. I'm sure that you do great work, and I'll see you in the next one. And all the viewers, thank you for joining in. Bye. Take care. Bye,
Thank
Anika.
you.
Yeah.
Yes, bye.